All right, let's get class started. Couple of announcements for you all. No Achieve Due Monday, so y'all have a little break after our midterm on Friday. I have office hours today at 1. I have to cancel my Wednesday office hours. We do have recitation at 8 a.m. still. And then I'll add a Thursday office hour at 2 o'clock. And then another reminder that our midterm is Friday. So about 30 questions, all multiple choice. I will provide you all with Scantrons. So you'll complete the Scantron and not write on the packet. This is how our final will be as well. You won't be writing on the actual packet with questions. You'll have scrap paper, of course. You'll have the same periodic table sheet that you had on the first exam as well. And then chapter 3 and 4 learning curves are available on Achieve. If you want to complete them to study and to earn the extra credit points, those will be due at the end of the day on Friday. Any questions about what's coming up, midterm, anything? Okay, we'll get right into it then. At the end of class last Friday, we briefly looked at this activity series of metals. One thing that you all should change here is that top left corner. It says metals difficult to displace. Let's change that to cations. Just to be more specific, these cations at the top of the activity series, when they are cations, it's difficult to reduce them to the metal, the neutral metal. Cations up there, they're going to stay cations. Down here, these metals are unreactive. These are difficult, the neutral metals are difficult to oxidize to ions. So we can use this activity series to compare, look at a solution of different atoms and see if that's going to result in an oxidation reaction based on what atoms are present. So a metal will transfer electrons to any cation that's lower on the list. So a metal, a neutral metal, a solid metal can replace a metal ion that falls lower on the list that's in an ionic compound. And then this metal activity series is an order of reactivity, so greater separation between metals, the more vigorous the reaction. So let's look at a couple of examples. The first one we'll do together, and then the second two I'll have you all try as iClicker questions. But here's a scenario. So we have a piece of calcium. A piece of calcium indicates we have a calcium solid that's added to solution with nickel 2 chloride. If we have solution of nickel 2 chloride, then we have nickel with a charge, so a cation, 2+ because it specifies nickel 2. And it's a solution, so we have aqueous nickel +2 cation. So the question is if a reaction is going to occur. When we put calcium in solution that already has nickel +2 cation there, will anything happen? Will the calcium give electrons to the nickel cation? We look back to the periodic, or not the periodic table, the metal activity series. Nickel cation is down here, and then calcium solid is up there on the periodic table. Calcium as a solid is a more reactive metal than solid nickel. Calcium then is going to donate electrons to the nickel +2 cation and form neutral nickel solid, and we'll get calcium 2+ cation after calcium gives electrons. So that means we will be changing what's present in solution. The nickel 2+ becomes neutral nickel solid, and the calcium will oxidize and become calcium +2 cation. So a reaction does occur. Calcium will replace or displace Okay, I'll start the next two iClickers. So using the same process, determine if a reaction is going to occur. Is the solid that's being added to solution going to displace the ion? One thing that's helpful to remember if we look at the activity series, the metals towards the top of the activity series are all towards the left of the periodic table. So the first two columns of metals, the alkali metals and the alkaline earth metals, are reactive metals that are often oxidized and exist as the cations. Everything lower is more to the right. They're all metals still, but they're further to the right of the periodic table. So generally, this is what you should remember for the assessments, is that metals to the left of the periodic table are more reactive. Now we're talking about the neutral metal. Neutral metals to the left of the periodic table are more reactive than metals to the right of the periodic table. There are some exceptions. We'll see one in one of these examples on the slide. I won't ask you about exceptions on the assessment. So you'll just want to remember, further to the left, that metal is more reactive than metals to the right. Okay, I'll give you all a few minutes to work on this. If you finish early, you might try the next page. So that's an exception to that general. So when you're doing this, it's okay if you want to any question. All right, let's say 30 seconds to a minute. Did you get logged in? All right, we'll end it here. And then let's see. All right, a little bit of a mix for the second one. So let's go through both of these together. First, we have iron pellets. So we have iron as a solid, and they're added to a solution of magnesium chloride. Magnesium, second column, 2+ ion. So question is, will iron as a solid be oxidized to iron with a cation, positive charge, and reduce magnesium to neutral magnesium metal? Well, if we go back to the activity series, magnesium is up here and iron is right here. So magnesium neutral metal is more reactive than iron neutral metal. That means magnesium will exist. If iron is present, it will remain as its cation. Iron as a solid will not displace magnesium as a cation. So for this reaction, there is no reaction. This third question, we have aluminum foil. So we have aluminum solid added to an aqueous solution of silver nitrate. We have silver with a +1 charge. Now I know why this one had more students that selected that there will not be a reaction, because if we look at the periodic table, aluminum is further to the right, so that should be a less reactive solid, and silver should stay with a positive charge. But that's an exception to the activity series. So this is an example of a question that will not show up on your assessment, but if you're working through the homeworks and Achieve, you should use the metal activity series. So this is an exception to the rule, the general rule. So aluminum is more reactive than, what's the other one? Silver? Than silver, even though aluminum is further to the right. No. No, you just need to remember metals to the left are more reactive than metals to the right.
Okay, so are we going to get any questions that are an exception?
No. No. Yeah. Other question? Do you have another question? Okay. So aluminum metal is a more reactive metal, more active metal than silver. So if we have silver as a cation present in solution and aluminum is added, aluminum will reduce the silver cation to be silver solid, and aluminum will be oxidized to aluminum 3+. So here a reaction does occur. Aluminum as a solid displaces the silver cation. Again, because aluminum as a solid is more reactive than silver as a solid. So aluminum will react, silver will remain a solid. Let's do a little bit of review of oxidation reduction reactions. This first reaction where we add calcium to nickel 2 chloride, let's write the balanced net ionic equation that occurs. We'll start by writing the oxidation half reaction and the reduction half reaction. This is an oxidation reaction. So in the oxidation half reaction, calcium is added as calcium with the oxidation state of 0, and it becomes calcium 2+. So that is what is oxidized. So we have calcium solid oxidized to calcium 2+ aqueous. Calcium solid lost 2 electrons, and so we represent that on the product side, where calcium solid lost 2 electrons. It separates, calcium as a solid separates into calcium +2 and then 2 electrons.
So do you know it's +2 because it got 2 from nickel?
That, and we can go based on its ionic charge. Calcium's in the second column, so it'll be +2. The reduction half reaction happens with nickel. So we start with nickel 2+. Nickel 2+ gains 2 electrons, and we form nickel solid with the oxidation state of 0. Now, if you remember from the question, we're adding calcium to nickel chloride. The chlorine is not involved in the redox reaction. So that is a spectator ion. And when we write the net reaction, we don't include our spectator ions because they'll be present as ions on both sides of the reaction. We already have balanced the number of electrons. Oops. So we are only canceling out the electrons. So our net equation, we have calcium as a solid plus nickel 2+ aqueous goes to calcium 2+, which is aqueous, and nickel solid. All right, the next few slides, there's really nothing for you to write down. We're just going to go over a few different specific scenarios regarding the reactivity of metals. So a lot of metals are reactive in the presence of H3O+. So H3O+ is if we have an acidic solution of water, the acid donates a proton to H2O, we get H3O+. If we go back to the activity series, you'll see that right here we have H3O+, H2O. All of the metals above this are more reactive than H2O. That means that if any of these metals, neutral metals, are in the presence of water, they will get oxidized. No, if they're in the presence of acidic water, H3O+, they will get oxidized to the cation, and then we produce water in that redox reaction. So as the metal is oxidized, water is reduced. We have an example here. We have magnesium as a solid in the presence of water that is acidic. There's also an acid present. Magnesium gets oxidized, and then water is reduced to H2 and H2O. Sodium and other group 1A metals react vigorously with water, even just neutral water. So here's an example of cesium and water. Here's a reaction. We'll form cesium plus hydrogen gas and aqueous hydroxide. So this vigorous reaction releases heat and produces hydrogen gas, and that's what can make this explosive. This reaction can be explosive. We have a lot of heat, we have gas. If cesium, neutral metal, is exposed to water, it produces a lot of energy in that explosive reaction. So neutral metals like cesium have to be sealed in some sort of container. If they're exposed to water, we have water vapor in our atmosphere. That can be a explosive reaction. Some metals are also oxidized by molecular oxygen, O2 gas, which is also present in our atmosphere. Almost all elements combine with molecular oxygen to form binary oxides. And the more easily a metal is oxidized, the more likely it is to react with O2 gas, meaning metals that are higher on the activity series, those neutral metals, potassium, sodium, etc., those are easily oxidized with oxygen gas. The least reactive metals, which are at the bottom of the activity series, are among the few elements that are actually found on Earth in their pure form. So those are copper, silver, and gold. We can find pure copper, silver, and gold naturally. Most other metals exist in nature as an oxide compound or as some other compound, not as its own individual metal, because it is reactive with oxygen, which is in our atmosphere, and water, which is in our atmosphere. So here's just a representation of that. These two groups of metals react easily with molecular oxygen. Copper, silver, and gold do not. That explains why we have silver and gold jewelry. Those are constantly exposed to the atmosphere. They're not reactive with water, with water or oxygen. And then copper as well is a common pure metal that exists in nature as a pure metal. A lot of metals, almost all other metals, react with oxygen to form insoluble solids. So aluminum, for example, if that's in the presence of water, that will form, this is supposed to be O2 as a subscript, and Al2O3, aluminum oxide, which is a solid. And then some compounds and non-metallic elements also undergo redox reactions with oxygen. We have coefficients here. Anything between or at the end, they should be subscripts. Sorry about that formatting. Forgot to make those subscripts. So you might change those in your PowerPoint to be subscripts. Okay, this whole unit, we've learned about a few different types of reactions, a lot of different types of reactions. So this question, we'll skip the second one. Try to identify what type of reaction is present. So you want to identify, we're comparing the last three sections, which were about precipitation reactions, acid-base reactions, and redox reactions. So you want to look and see what reagents you're starting with, if they will undergo a precipitation reaction, redox, or acid-base. So I'll give you all a few minutes to start working on this, and then we'll go through it together. Sure. Here, Ellie. If you don't know where to start, try writing the products first. Think about how those two reactants would react with each other.
Oh, yeah.
Say one more minute, we'll start going through them. All right, let's go through these. So this first reaction, here are the things that I would expect you all to be able to do. So I expect you all to look at these two reagents in the first reaction and recognize that they are ionic compounds. So we have silver, you should also know the charges. So we have silver with a +1 charge, and the nitrate polyatomic ion, you should also know the name of that, with a -1 charge. Then we have sodium chloride, sodium +1, chloride -1. We have two ionic compounds. They undergo a double displacement reaction. So that means that we repair the cation and the anion. So we have now silver chloride. We need to now check if these new compounds are aqueous or solids. So silver chloride and sodium nitrate. Actually, let's start with sodium nitrate. This is another thing I would expect you to remember. This is covered under the first solubility rule. Group 1 metals are soluble, and the nitrate is one of the anions, one of the polyatomic ions that are always soluble. So you should know that sodium nitrate is an aqueous. And then next we have silver chloride. This is not what I would expect you to remember. This has an exception to the rule. Silver with halogen, these are insoluble. So I won't ask you a question about silver with a halogen on the assessment. But as you're working in class, working on your homework, you can use the solubility guidelines and you'll see that this is a solid. So then what type of reaction is this? Yeah, precipitation. Okay. So we have a precipitation reaction. Another thing you should be able to do is write the net ionic equation. You can do that by writing the total ionic equation where you separate every aqueous compound into its ions, keep the solid together, and then cancel out any ions that are repetitive on the reactant side and the product side. You could also look at the solid. We know that for the net ionic equation, we keep the solid together. On the left side of the equation, we should have the ions that form the solid. So we should have silver plus and not nitrate, chloride minus. And that's the net ionic equation. So you can use either method. Questions about that one? All right, next reaction, we have sodium hydroxide and hydrogen with the acetate polyatomic ion. So here, when you see sodium hydroxide, you should recognize that as a strong base. You see a strong base, then you might want to check if the other compound is an acid. So we have sodium and hydroxide with a group 1 or 2 metal. Most of those are strong bases. And then we have acetate polyatomic ion with hydrogen, which means we do have a hydrogen cation. So if you have a hydrogen cation, hydroxide anion, these two will combine. We're doing another double displacement reaction, but the hydrogen and the hydroxide combine to form water. We have an acid and a base. This is an acid-base reaction. The other product is sodium acetate, so NaCH3CO2. All right, and this last reaction, we just learned that group 1 metals combine with molecular oxygen to form metal oxides. We have a group 1 solid metal and oxygen gas. These are going to combine. We have a combination reaction to form K2O. We know the formula by using the charges of each ion. Potassium typically has a +1 charge in a compound. Oxygen is -2, so we need 2 potassiums for every 1 oxygen. So you should be able to do that. We have calcium as a solid, which has an oxidation state of 0. Oxygen as a gas has an oxidation state of 0. I think I just said oxidation. Oxidation state of 0. In potassium oxide, oxygen is now part of a compound, so it has an oxidation state of -2. Potassium has an oxidation state of +1. We've changed the oxidation states of both reactants. Oxygen has taken electrons from potassium. We've transferred electrons, so this is a redox reaction. K2O is aqueous. I think based on our solubility rules, we have a group 1 metal, and I don't think there are any exceptions to group 1 metals being aqueous, being soluble. All right, questions on any of these reactions? Or other chapter 4 content?
So would you have to balance like the last reaction?
Yes, good point. We forgot to balance. So all of the other reactions were already balanced, but this one is not. So if we form K2O, well, if we look at the oxygens, we have 2 oxygens on the side, only 1 and the reactant. So we need a coefficient of 2. I'm sorry, only 1 in the product. So we need a coefficient of 2 to have 2 oxygens produced. Now we have 4 potassiums produced. Potassium moles, we need a coefficient of 4 in front of potassium here. Other questions? Okay, we will get started with chapter 5 then. So let's open up the chapter 5 PowerPoint. Oops. All right, chapter 5 is all about stoichiometry. So stoichiometry refers to the calculations that we do to determine how, if we have a certain amount of reactants, how much product can be produced. We can calculate the number of moles, the mass, number of molecules, or if we're desiring to produce a certain amount of product, how much of the reactants do we need to add to the solution or to the reaction. So the first few sections are calculations. We'll do mole calculations for chemical reactions, mass calculations. We'll talk about problems involving limiting quantities, and then theoretical yield and percent yield. You may have covered some of this or all of this in your lab already, but if not, we'll go through everything anyway. And then we are going to talk about molarity, so concentration of certain solutes in solution. And then lastly, we'll talk about titration reaction or titration lab technique. So again, as always, list of learning outcomes for chapter 5. And let's get started with section 5.1. So we will calculate the number of moles of any substance involved in a chemical reaction given the moles of another substance. So let's start with defining stoichiometry. That's all this is here. This first blank is just the word stoichiometry. This is the calculation of quantities of any substances involved in a chemical reaction from the quantities of other substances. So as long as we know quantity of one substance, we can determine quantities of the rest. So stoichiometry refers to the ratios of substances in a balanced chemical reaction, or in a chemical reaction, and so this requires that we have a balanced chemical reaction. So anytime we're doing stoichiometry, if your reaction isn't balanced properly, then you won't be doing the proper calculation. So you have to make sure first that the reaction is balanced. Here's an example of a balanced chemical reaction. We have phosphorus solid, chlorine gas combining to form phosphorus trichloride. Based on this chemical reaction, we can interpret this in two ways. We have 2 atoms of phosphorus combining with 3 chlorine gas molecules, 3 molecules of Cl2, and those produce 2 molecules of phosphorus trichloride. So we can talk about individual atoms and molecules, or we can talk about molar amounts. So 2 moles of phosphorus react with 3 moles of Cl2, and they produce 2 moles of phosphorus trichloride. In most of these calculations, we're using this molar ratio. So we have a figure, and then we'll do a learning check. So as long as you have your balanced chemical equation, you have formula units of some reactant A. You can use the balanced chemical equation to determine formula units of some reactant B. Or if you know moles of A, you can use balanced chemical equation to determine moles of B, some other reactant or product. And then if you want to convert between moles of B in formula units, you use Avogadro's number, and then same thing for the other reactant. So let's do this question together. We'll calculate the number of moles of aluminum that will react with 3.18 moles of oxygen to form aluminum oxide. So here we have a redox reaction. Aluminum is oxidized and oxygen is reduced. It's already balanced for us, so we use the balanced chemical equation to determine moles of aluminum that will react with 3.18 moles of oxygen. So we start with the quantity given. We have 3.18 moles of oxygen, O2 gas. And then now we're using this balanced chemical equation. We know for every 3 moles of oxygen, 4 moles of aluminum will react. So we can convert moles of oxygen by canceling out moles of oxygen using the ratio of coefficients here. So 3 mole of oxygen is reacted for every 4 moles of aluminum. And these are the coefficients in that reaction equation. So if we have 3.18 moles of oxygen, we use this conversion based on the balanced chemical equation. This will result in 4.24 moles of aluminum reacted for every 3.18 moles of oxygen. And all we're doing here really is using that balanced equation to convert moles of one substance in the reaction to moles of another. Let's do another one here in the next slide. We have hydrochloric acid reacting with metallic calcium to form gaseous H2 and aqueous calcium chloride. Calculate the number of hydrogen molecules, H2 molecules produced from the reaction of 7.50 moles of HCl. And we're assuming we have enough calcium to react with hydrogen chloride or hydrochlorous acid to produce H2. Now, if we look at our chemical equation is not balanced. So the first thing we need to do always is check the chemical equation and make sure it's balanced. We have 1 hydrogen on the reactant side, 2 hydrogens on the product side. So we need a coefficient of 2 in front of HCl. We now have 2 chlorines on the reactant side, 2 chlorines on the product, so that's good. and then 1 calcium on the reactant side, 1 calcium on the product side. So we're good. We just needed that one coefficient there. All right, so we have 0.750 moles of HCl, and we want to know how many moles of hydrogen gas is produced. So 0.750, we start with the quantity provided, 0.750 mole hydrochlorous acid. For every 2 moles of hydrochlorous acid, we form 1 mole of hydrogen gas. So we use that comparison, the ratio of coefficients, to convert from moles of HCl to moles of hydrogen gas. Now you can see if we hadn't balanced the equation, we would not have a 2 here, and we would not get the right answer. We need that balanced equation to have the proper ratio here. So if we start with 0.750 moles of HCl, we know for every 1 mole of hydrogen, we need 2 moles of HCl or for every 2 moles of HCl, we produce 1 mole of hydrogen gas. Then we have 0.375 moles of H2 produced. That's not actually what the question asked for. The question asked for the number of H2 molecules. So we need one more conversion. We're just using Avogadro's number. 0.375 moles of H2 are produced. And then we convert using Avogadro's number. For every 1 mole of H2, we have 6.022 times 10 to the 23rd molecules of H2. So we have 2.26 times 10 to the 23rd H2 molecules. You do not need to separate this into 2 equations. You could start with 0.750 moles, use this conversion, and then use this conversion, and you can go directly to number of molecules. That's fine as well. Okay, next slide. Another learning check. The iClicker here. No, we'll do this on Wednesday. We'll wait. But the first question is balancing the reaction. So you could try that now. And just keep in mind that will help for the midterm because you also need to balance reactions on the midterm.